Hello, physics people. So here is a video, and we're going to talk about resistance today. And when we talk about resistance, we're looking at like resistance inside of a electrical circuit. So inside an electrical circuit. So we talked about current. So current would be those flow of electrons that are going through a circuit to light something. But today we're talking about resistance. Like what is resisting that current from moving around? Because it's not going to move at an infinitely uh, a fast pace. So um, resistance is really like the root of like how we generate this power to light a light bulb or to power your toaster oven or your how you charge your cell phone. Okay, so one of the easiest ways to think about this is I like to put it into a river analogy. So you can think of the circuit as this river, this wire is this river where current can flow. So let's draw some current in here. So we got current, so the water is able to flow through here. And remember, this is just an analogy with water. So we got this water going through um, this riverbank. So here's the side of the rivers. Well, here's the question. What would cause more resistance to flow, or what would cause more resistance to the flow of the water in a river? So what can you do to slow that current down? If you think about that, what's something you can do? Well, I think one of the when I ask this question to students, one of the first things that they say is like, "Oh, well, you could throw a big rock in the river, so we could put something in that river to slow that current." So that's completely correct. Yes, you can do that. So that would be resistance. Also, where in this river would there be the most resistance to flow? You might think like right here, right? Like it's got to go through this tiny bend in the river, so it all has to go through this tiny spot. So that's going to resist that current flow. And that last thing, this one's a little bit trickier to see, but if you think about it, like what else would cause more resistance? And that would be how long that river is. So if that river was really, really long, um, then there would be more resistance to that flow. Okay, let's take that and let's put that into terms of um, like looking at those factors in terms of a wire. So we just said that length of the river. So if you have a really long wire, you're going to have more resistance than if you had a really short wire, right? So that makes sense, right? The electrons are going to flow through the short one at a quicker rate. Okay, so the length, if we increase the length, we increase the resistance. We increase the resistance. So increase L, you increase R. Okay, what about area? So area in that river analogy, that's like where, like whether it comes to like a bend or like where it presses together. Um, so you can think of like a garden hose. If you had a big garden hose, then that's going to let more water flow through than something that was smaller. And so we call that the area. So and technically it's a cross-sectional area. So here for this one, it's a circle. So we have, if you're thinking about a circle, we got pi r squared here. And this one would have a smaller area. So if we have, hey, think about this. If our area increases, what happens to the resistance? It decreases. It decreases. So this is called inversely proportional. Was as the area increases, the resistance decreases. Up here, the length, as the length increased, the resistance increased. So that's directly proportional. So that's really, like, these are really important when we start to like think about the equation, like if we were to put all these together in the equation. Okay, and the last thing, this one is, this is the, like, remember you could throw more rocks into the river? Well, that's kind of what the river is made of, like a bunch of rocks and stuff. So in a wire, really we look at like, what is the wire made of? And that has a certain characteristic, and we give it a special name and we say like, oh, that wire would have a certain resistivity. So new term here, it's new vocabulary of resistivity. Sounds technical, but it's really not that hard. So let's look at resistivity. Okay, resistivity. In physics, a lot we give things variables to represent them. So in this case, the variable is it's a Greek symbol and it's called rho. I'm not sure if like it's the Greek symbol is actually spelled like that, but that's how you say it, is rho. Okay, so we have the resistivity, and remember that's how easily a current can flow in that material. So like think about if you have a wire, you guys might know this, but like if you have a circuit, a lot of times that wire is made of copper. So copper is like a really common thing to make wire out of. And so you might think like copper, that's the best thing to create a wire with so that current can flow through. But actually silver is a little bit better. So silver, you might think like, wait a minute, why don't we make all of our wires out of silver? But silver costs some money, so we don't do that because it would be crazy expensive. So all right, the resistivity. So is silver have a greatest resistivity? Well, actually, it would be less because you can think of resistivity like silver is going to have a really low resistivity, meaning that the current can flow really easily. And lead is not as good of a like, you wouldn't want to make a wire out of lead because electricity just doesn't flow, current doesn't flow as well through that. So copper has less of a resistivity than lead. All right. So let's put all those three variables together and come up with an equation. So here we go. We have this equation right here. And really, you can just get this equation from just what we said. We said that if you increase the length, well, think about that. You increase the length, you increase the resistance. They're both directly proportional. If I put a 2L, if I double the length, I double the resistance. All right. What about area? Well, we said that area is inversely proportional. So if I increase the area, it's on the bottom of the fraction. So that means it goes down. Think about that. If I put I'll do this in red because it's a little easier to see. If I double the area, then the resistance goes down by half. If I make it bigger, the resistance goes down. And the last one, we said resistivity, that's directly proportional. So if we have a low number here, say we have like a low number like silver, well, the resistance is small. If I make that lead, well, the resistance would be a little bit more. So I'll just, to wrap it all up, I'll just read this out. So we're reading this equation. It says resistance, the R, is equal to, there's my equation, to the resistivity, this rho right here. So this thing, the resistivity, times the length, how long that wire is. And we're going to divide that by the area of the wire. So that area. Okay, that was a quick talk on resistance. So hopefully you guys get it. And of course, if you have questions, you can you can contact me and we can ask and we can straighten everything out. Okay, good job.